Hi everyone, hope you had a great weekend. This is a video to help you learn from your mistakes on your last test, which was on Newton's third law. We're going to start off with the first problem. The first problem gave you two different pictures and it asked you to draw a force pair between the two objects in the picture. In order to jog your memory and help you remember exactly how to draw a force pair, I have two objects here at my table. I have an acorn squash. If any of you have never ate an acorn squash, it's quite delectable. It looks like this. An acorn squash and a knife, because in order to eat acorn squash, well, you've got to cut into the acorn squash. So here's a force pair. Okay, that's two objects. The objects are touching. And when we draw a force pair, we'll draw the two objects touching like this. And the couple things we want to remember. We need to have two arrows. One, two. Both of these arrows need to be labeled using F for force, and then the object's name right underneath it. Okay? So I have F knife and F squash. Some of you forgot to label your arrows, and if you don't label your arrows, I don't know what type of force you're talking about. So that's really important, especially as you go on in science. If you were curious about the two planets problem, the two planets, when they are coming together like this here, you want to make sure that those two forces, even though the planets aren't touching, the force of the gravity between the two planets is there pushing on each other and pulling on each other. Technically it's pulling because they want to pull each other towards the other planet. Okay, so you'd want to draw the forces with the arrows meeting in the middle and still labeling those two. All right, first problem done. Let's go to the second one. The second one we had some more issues on. So we had 4 different types of balls, 4 different ones, and you had a squirt gun. I don't really have a squirt gun with me, but I do have a glue gun. This glue gun is going to model your problem, okay? I also drew a picture so that you could see. So here we have a squirt gun on this side. We have a basketball here, a tennis ball, as you've been using in your labs, and then a baseball, okay? And then last but not least, a little tiny marble. If my squirt gun is 1 meter away from all of these objects, and I squirt them all with this water gun, okay, they should be getting the same amount of force. So here in my example, if I give all of the balls the same amount of force with my squirt gun, I can have a ball with less mass being squirt and a ball with more mass being squirt. One of the points that you were supposed to get is the water applied a force to each object, and each object applied a force to the water, but in an opposite direction, okay? So even when the water squirts and hits the ball, even if the balls have different masses and different sizes, every time that that water squirts onto the ball, it's going to push on this ball with an equal and opposite force, okay, as the ball pushes on the water with. That's weird. I know it's strange, but when this, again, we'll say it one more time, you squeeze water out onto the ball, and the ball pushes back on that water with an equal and opposite force going the other way. Just like you saw that picture with the acorn squash and the knife, okay? If a ball has more mass than another one, the ball with more mass won't roll as far, even though it's being pushed with the same amount of force, and it's pushing back with the same amount of force. If something has more mass, it's harder for it to move. Now, if it's tinier and has less mass, okay, it's going to roll away because the water is going to push it, because if you have less mass, you can accelerate more, okay? Because that's that thing with the conservation of momentum. If you're still confused on problem number 2, come and see me. Raise your hand and ask me a question. Let's move on to problem number 3. So in the different tests, we either had soccer or volleyball. I'm going to talk about soccer, but the volleyball, the same idea is still applied to the volleyball one. In the soccer one, in one of the tests, it asks you if you kick a bowling ball versus a soccer ball, okay, what can you say about the force pairs between these two objects, okay? Well, it's sometimes easy to think about the object with more mass, like the bowling ball. The object with more mass, we would think that the foot would put a larger force on the ball. But earlier on in the test, on that problem, it says that each player kicks the ball with the same amount of force. Okay, now that we know that, the heavier ball, the more massive ball, is not kicked with more force. They're both kicked with the same amount. It's really important that you get that the foot, right here, the foot puts an equal but opposite force on the ball as the ball pushes on the foot. So they both push on each other with the same amount of force on the bowling ball and on the soccer ball. One of your last questions asks you, why does the soccer ball move further than the bowling ball? Why does it accelerate away further? Well, that has to do with the fact that the soccer ball has less mass, okay? So when it gets pushed by this foot and it pushes back, the foot has more mass than the soccer ball, okay? So it doesn't accelerate as much going this way. The ball, because it has less mass, it has a larger acceleration. Remember, force equals mass times acceleration. So it's going to shoot that way, a lot more than the bowling ball would. What we can say about each of these force pairs, that they both objects push on each other with the same amount of force, but they both do different things based on their mass, and that affects their acceleration. Okay, your last problem, your last one. This one is the save the world problem. You had Earth up here, and you had a meteor, okay? We're always in risk of getting hit by a meteor, and that meteor was going straight towards Earth, and your goal was, how do I get this little meteor to go 10 meters off of its path so it won't hit the Earth, and it won't get in Earth's orbit, and it won't go flying towards our crest and kill us all, okay? So I drew a little picture of that for you because a lot of people thought of this idea. Some of you didn't, some of you were really ingenuitive. I got some crazy ideas like, well, I could make a giant metal baseball bat, or I could put some giant Nike shoes that would kick the rocket. I think I had wrap the Earth in foam, some just different really creative ideas, and those were really fun to read, so thank you. But a lot of people thought about the Earth, the meteor, and some kind of missile, rocket, or another meteor that could be shot and hit the meteor here to push it off in a certain direction, okay? And this is a great starting place. In your solution, that's where you could be really creative, but when it asks you, Newton's third law is used this way, I wanted you to explain to me how your idea has to do with Newton's third law. Where a lot of you had a little bit of issues was that with this meteor thing, the meteor needed to have a smaller mass than the object that you were pushing the meteor towards. The reason for that is because if they both have the same mass, they're going to bounce back and accelerate in that direction, and you want to make sure that this meteor gets really far away from Earth. So it needs to have more of a mass in order to have a bigger acceleration away. Also, if you shot this rocket off, or sent a meteor off, or a missile from Earth, and it was going towards the meteor, if it's not at the correct angle, this is being a little bit more detailed here. If it's not the correct angle, the missile, rocket, or meteor is going to go back towards Earth after it hits the meteor and also hurt Earth, okay? So that's an extra layer of detail that I wanted you to think about, okay? So that we need to make sure that we hit it from the right angle so that they both bounce off each other and we're not hit by either object. The last problem on the back page, this is the advanced understanding problem. It asks you to think about our lab. We were trying to get a tennis ball into a taped square on the ground, especially into this little taped area here. That was the challenge, the gold medal challenge. The first part of the problem, it asks you, how could you use Newton's first, second, and third law? How could you apply that to get the tennis ball actually in the little tiny square? Newton's first law says that if something is moving, it wants to stay moving unless acted on by a force, okay? So a force could be here, it could be my hand stopping it, okay? If I roll it along a table, this ball will eventually stop due to friction or air resistance. That would be another force that could stop it. But Newton's first law also says that things that are still like to stay still, right? Unless acted on by outside force. And our ball initially was standing still on that black piece of tape. And you had to tap it with that car. So what I was looking for is, well, the ball was still and we had to get it into the tape. So we ended up hitting it with our car, tapping it, and it flew forward because a force acted on it. Or in order for that ball to stop in the little squared tape area, I needed to apply the appropriate amount of force so that the force of friction could stop that ball as it was going into the square. Newton's second law application. How can I apply Newton's second law? Well, Newton's second law says force equals mass times acceleration. And I needed to know, with the mass of my tennis ball, what would be the appropriate amount of force to give this tennis ball so it could accelerate into that square, okay? I thought that maybe some of you would think that with the fan in the car, that's more mass than the tennis ball. So when the car hits the ball, more mass, causing the ball with less mass to accelerate this way and go in to that square that's taped off here. The other thing is that you could say is that, well, we needed to change the amount of force in order to know how far to accelerate the ball, okay, depending on its mass, if its mass is kept constant. So you needed to change as you did your experiment. Finally, Newton's third law application. This is the one we just learned about, and this is if you have those two objects, here's my other ball. If you have two objects, they push on each other, okay? They push on each other with an equal and opposite force, or object A pushes on object B with the same amount of force no matter what their mass is. Either of those, if you can explain both of those, you are on super high level. Okay. You make a force pair with your hand when it touched the car. Pretend my little blue physics car is here. That's a force pair. And also when the car touched your tennis ball. That was another force pair. Without those force pairs, we could have never got the car moving, right? And without the final force pair of the ball stopping on the ground here, we would have never got the ball to stop. So everything we do in life often has a force pair, and it's pretty cool when you learn that, and it changes the way you look at science. My last thing for you is, if you've got to this end of this video, I have some Stanford pom-poms. I'm wearing my Stanford sweatshirt for you. So great job. I'm so proud of you. I'm cheering you on. I'm here to help. If you have any questions or you're still confused, please raise your hand and talk to me. At this point, what you should be doing is working on your learning from mistakes sheet. It looks just like this. Okay, just to go over it really quickly. The first part asks you to rewrite or paraphrase the question that you got. Explain what made it difficult or what you didn't understand here. The third step says show the correct answer to the question you mixed, right here. And number 4, how do you know this answer is correct? Here. Number 5, write a new question with the information you missed. Number 6, write the answer to your question. And then finally down here, get the problem checked by me or another student. Okay. And on the back, it has room for another question you missed. For every question that you missed that was a little confusing, I want you to do this. I want you to think about this process. This process is tried and true, and it usually helps people get a greater understanding of something they didn't understand before a test. And when you go take the retake tomorrow, you'll be way more prepared and actually have a deeper understanding, a real understanding, as you go on and take that test.